Good morning, everybody. Thank you for being here. My name is Danilo, and I'm technical evangelist at Amazon Web Services. And today I'd like to talk about one of the topics that I'm more passionate about. It's machine learning. And I think this is really important. Machine learning and artificial intelligence are going to change the way we live and we work in the next few years. And I think developers should be aware of the capabilities that are coming. So just to start with the right foot, I'd like you to look at this picture. And does anybody know what's going on in this picture? So this is a picture from London in 1939. And these people was counting by hand something like 8 million tickets from the underground systems to understand the usage and plan for the future expansion of the underground in London. So when I see these heroic efforts, I really think that now that everything is digital, we don't have no excuses as developers to use the data to improve the user experience, the capabilities of our applications. And the idea is that often we have this situation when we have some data and we want to build some predictions out of this data. And the way to do that is to build a model. The model is the part of the architecture that is capable of abstracting from the specific data points that you collect and to be able to create prediction for new data points, maybe something that is going to happen in the future. And how do we build a model? So this is probably one of the first software computer models that was built in 1959. This is Arthur Samuel, and he created the first program that was playing checkers. And in the first releases, he was focused more on searching in the solution space of the possible moves that you can do when you play checkers. And then in the third version, he also had the idea of having the computer program challenging and competing against itself to discover new moves, discover better alternatives. And of course, he created a program that was better than himself in playing this game. So I think this is an example of learning, because you create something that, as a developer, that is better than you in doing that thing. And Arthur Samuel is considered the father of machine learning. And machine learning is a part of artificial intelligence, and it's quite a broad topic. So I'd like to start setting some terminology. When you talk of machine learning, most of the times you talk about supervised learning. And by supervised learning, we mean when you want to infer a model from labeled data. And by labeled data means data that has a label, a value that then you want to predict. So for example, if you want to build a plan for the underground in London, you take all the tickets that tell you where the people was using the underground, and then you can use this to create prediction and say where the people will use the underground in 1 month, 1 year, to understand if the underground lines can sustain the growth. Or for staying maybe in the public transport systems, for bike sharing. If you are a town, you have maybe a nice bike sharing system when people can rent bikes and can move around in a green way and stay fit. You may want to know how many people is renting those bikes every day, so that you can know how many bikes you can repair every day without disrupting the service, or how many bikes you need to buy to sustain the growth of the service. On the other side, we have unsupervised learning. This is data without labels. So for example, your customer data, if you have customers, maybe you have 1,000, 1 million, or 1 billion of customers, if you're Facebook, and these customers have some information, but it's really hard to understand which is the label that you want to use. And that's the reason why unsupervised learning is often a little bit behind supervised learning in the commercial use cases. There's a third category that sometimes is considered part of unsupervised learning. It's called reinforcement learning. It's when you want to reach a goal with your model in a dynamic environment. So for example, if you want to have a vehicle that is self-driving, even if you teach to the model how the streets are done, how the traffic lights are working, you still will have other vehicles moving around, pedestrians crossing the street, so you need to have a continuous feedback that gives a reinforcement to your learning and updates the model in real time. Or still is reinforcement any example of game. So unless you explore all the possible moves of a game so that you really know everything that can happen, you still need to understand which is the other move. So checkers, again, is an example. Chess is another example, but also dynamic games like if you want to create a robotic tennis player, you must understand where the ball is going and project the trajectory in his mind. With unsupervised learning, over the years, the most common example that we found was clustering. And by clustering, we mean the creating groups of the data points you provide. And this is used very much by companies for clustering their customers. So if you have lots of customers and you can talk to all of them, you want to create categories and understand in which category your customer is. So, for example, this is a bidimensional example of clustering, and it's very easy for us to look here and find that there are these 3 clusters. But you have to think that normally when you do clustering, you don't have 2 dimensions, but you have hundreds or thousands of dimensions, all the possible information that you can collect, for example. And it's not so obvious to visualize points and finding clusters. So, for example, this can be, if these are your customers, on the x-axis, you may have their capacity of spending, so how much this customer can spend for products that you sell. And on the y-axis, you may have how much they actually spend with you. So this is usually called the share of wallet. So in this case, the customer in the top right, they have some capacity of spending, and they spend almost everything that they have with you. So from this customer, you want to have a retain strategy. You want maybe to help them use your service, but you don't want to go to them and sell other things because they're already spending everything with you. The customer in the bottom, on the other side, they have a capacity of spending that is greater of what they spend with you, so maybe you want to engage them and maybe send some promotions. And this is what companies do. They understand with clustering the categories of customers, and in this way they understand where to try one kind of promotion or another. Another example of topic modeling is, unsupervised learning is topic modeling, and this comes into natural language processing. And this is an interesting algorithm. If you have a large collection of documents, topic modeling can extract the top topics that are recurring in those documents. And there's also a nice open source library, it's called GenSim, that you can download. It works with Python, and you can, for example, try that with your emails, and it's quite nice to discover what your emails are actually talking about. With supervised learning, so when you have labeled data, usually you do these 3 things. You may want to do regression, so you want to guess a natural variable, some number. So for example, how many bikes will be rented tomorrow? So 1, 0, 100,000. Or you want to do classification. The most common use case for classification is binary classification, when you have 2 categories. And most of the email clients nowadays, they use some kind of this of machine learning to understand if one email is spam or not. They're not always right, but they learn and they usually do a very good guess. So is this email spam, yes or no? Or any case where you have a true-false category, this is also binary classification. Normally, under the hood, the algorithms, they don't actually give only a 1 or 0 or a true or a false. They usually have some percentage of possibility. So sometimes it can be interesting not to just get the true-false output, but to look into the probability. So maybe this email is classified as spam, but maybe the probability is 55%. This other email is classified as spam, but the probability is 95%, so probably this is really spam. And you will see normally you want to set a threshold on this probability. It's not always 50%. With multi-class, you have multiple categories. So sentiment analysis, for example, on social media, on tweets, has evolved a lot. So in the past, sentiment analysis was only looking into positive or negative sentiments. But nowadays, you might want to look for multiple classes. So maybe a comment or a tweet about a company can be happy, can be sad, can be angry, can be confused, can be disgusted, can be surprised. All these are different categories. Most of the times, multi-class classification can be built on top of binary classification. So you just do binary classification on all the categories. So is this happy or not? Is this sad or not? And so on. And then you take the one with a higher probability, and that's the class that you choose, because probably if sad is 95% of the probability of being sad, and all the others are much lower than 95% probability, sad is the right category for this social comment or this tweet. And when you have a supervised learning model, when you want to train the model, technically what you are actually doing is to minimizing the error, because you have the real data, you have the labels, so you can measure if the model is working correctly or not, and you can measure this as an error function. And this error function is the one that you want to minimize when you do the training of the model, so you want to build and find the right parameters that your model will use to do the predictions. But there is a very important phase when you do the training of the model, that is the validation, because with machine learning it's very easy to create very complex models that work very well with your own data, and then when you start doing prediction, they give completely outside of any reasonable sense answers. And why is that? Because you have this labeled data, and if you train the model on this data, there will be a bias. Like for people, if you only know something, you will be biased into what you know. But you want your model to work outside of this labeled data. So the idea is that you can split this data into two subsets. Usually you have 80–70% as training, and the remaining 20–30% as validation. And then you use only the training set, so 70–80% of the data for training the model. So you measure the error of the model on this subset of the data, you try to reduce the error, and at some point you will get a good result. And then you take this model and you apply this model on the validation set, where you know the right answer, because it's still labeled data. And you can check if the error remains the same. So maybe you have 5% of error on training, you apply on validation and you get 5.5, so probably it's okay. But sometimes it happens that you take the model on the validation and you take a much higher error. That means that the model is not capable of abstracting from specific data points to new data points, so it's not working very well. And this happens because it's very easy to run into this problem, overfitting. So let's think that these are data points that you want to use to build a model. So maybe this is the number of bikes that are rented during a day. So on the x-axis we have the hours, and on the y-axis we have the number of bikes that are rented. So you may try with some very complex model that can be a polynomial of high order, and you get something like this. This is a very good fitting, because it's a complex curve that is going through all the data points, and then I can start to do predictions. Because I can say, okay, what happens at this time of the day, and what happens at this other time of the day, and I can find that roughly the same number of bikes, if this is the bike model, are rented, and this is some value that I get. But actually data in reality, and people that comes from scientific backgrounds, they know it very well, is never clean. There's always error, fluctuations. So a much simpler model that goes through all the points with some small error is much a better fitting. So use simple model if you can, and then if you see that the simple model doesn't work, then try to make it more complex. And as you see, you get much different results from this model. That's why validation is important. You don't want to discover this when you're, for example, in production. One way to reduce overfitting is also called regularization. And there are different techniques. So the idea is to add a cost for using more complex models, so more complex and larger parameters in your model. Usually there is L1, L2 regularization. They basically are some constant multiplied by the sum of the parameters, L1, or the square value of the parameters, L2. And in this way, you can have another additional number that you want to reduce. So you want to add this as a penalty for your model. Another point that you must be careful about, some platforms, they manage this out of the box, but it can be tricky, is normalization. So if you have multiple variables, some variables may be numbers that are bigger than others. So for example, I may have, in my bike sharing model, I have maybe the hour of the day, and this will be forced to be between 0 and 24 and 23, or 1 and 24. And maybe I have hundreds or thousands of bikes. So numbers that are bigger in a mathematical formula will automatically become more relevant and will weight more in your model. So to avoid this, usually you want to scale all the values that you have. Can be time, can be numbers of bikes, can be the weather conditions, the temperature of the day, in the same range, for example, between 0 and 1. And then you train the model with all the variable normalized into this range, and then you can get the prediction, and then you denormalize the value to the actual value, so you get 0.5, but this actually was a temperature, so I want to get it back to 25 degrees, for example. So this is very interesting. You should look if you need to do normalization or not. It depends on the model you're using, but it's always interesting to have a look. And I always talk about how each model has the internal parameters that you want to change with training, but there are also other parameters that are inherent in the choice of the model. So when you create a model, you can choose one model or another, and every model can have parameters. For example, L1 and L2 that we saw here, you usually have some constant in the front to add more or less cost for regularization. And these are usually called hyperparameters because are parameters outside of the model that still can have a choice. In this case, normally what you do, you create 3 sets of labeled data. So you have your training set, and then you have your validation set, and then you have another test set outside of this. And then you basically try your first hyperparameters with you train your model, and you get your result with the validation. Then you try other hyperparameters, you do the training and test the validation. And you iterate on multiple hyperparameters. And then when you get the best result, you still need to test it on the test set, because otherwise you can get a bias. You can get a model that works better only on that specific validation set. So you test on another set of data to be sure that the model still is capable of working outside of specific data points. So the idea is that you iterate on those. And more generally, there's the idea of cross-validation. So if you have some data, since usually you don't want to waste any data, you can just split your data in multiple sets. And then the first time you use the first set for validation and the other for trainings. And you get some result. Then the second time you take the second set for validation and all the other for trainings. The third set for validation and all the others for trainings. And so you use all the data scrambling around the different sets that you decompose the data into. But this is classical machine learning. And what we've seen in the recent years is a lot of interest into neural networks. And neural networks are really changing the game for machine learning. So most of the great advancements that we saw in the latest years come from neural networks. But actually, neural networks are not a new concept. So this is probably the first idea behind a neural network is the idea of threshold logic units. It comes from 1943 from McCulloch and Pitts. This is their paper. These were the years when we started to understand how our brain works, how our neurons works. And our neurons, basically, they receive a lot of signals from other neurons. And if these signals go above a certain threshold, the neuron will fire the signal toward the other neurons it's connected to. So each unit is simple, and they decided to create this new logic unit. So normally logic units at the time that were built in hardware were AND, OR, XOR. They were really built in hardware and assembled to create what was a computer of the time. The idea to extend the concept and create a threshold logic unit. So not an AND that works only if 1 and 1 goes in and you get a 1 output, but a threshold logic unit where you have a threshold. If you receive multiple inputs that go beyond some threshold, then you fire a 1, otherwise you have a 0. Then this concept was moved forward and formalized more by Rosenblatt in 1962. This is a very important white paper for neural networks. It's the principle of neurodynamics. And he created this idealized concept of perceptron. This is really the mathematical definition of how this mathematical idealization of a neuron should work. So you really have a lot of inputs. This can be, for example, a pixel of an image, or can be part of a speech that is recorded digitally. And these inputs are multiplied by some weights, and these weights, the W1, 2, and 3, and so on, those are the weights that you want to learn in your model, are summed together. There is also a constant weight that you add. And if this goes above a certain threshold, you fire an output, otherwise it's at 0. So mathematically, this is usually a threshold function. And the threshold function is interesting because over the years we experienced different threshold functions. At the beginning, they tried this really steep one, then they tried to create a smooth one, like a sigmoid or an arctangent that can be, where you can have a derivative. This is important mathematically to train the model. And then we found that some very basic functions like 0 or 0 if less than 0, or x if it's above 0, it works very well. So now we are trying different functions. So you get the input, you have the weights, and you have what is called the activation function that decides if this perceptron gives an output or not. Problem was that in the 60s, other people working in AI, they didn't agree with this model. They mathematically proved that the perceptron can only solve linear problems, so very simple problems, and people started to lose a little bit of interest. Of course, people start to have the idea, okay, maybe we can try to put more perceptrons together, so we can create multiple input, multiple layers of perceptrons. They are all connected together. Each of those circles here acts as the formula that we saw before. And in this way, we can go beyond the linear model, because when you start to combine multiple functions that are not linear, because the activation function is not linear, this is not linear, can solve more abstract problems. Problem is that training this model starts to be very, very complex, difficult to do, both from an algorithmic point of view, there wasn't the mathematics to do that, and also from a computational point of view, it was very complex they didn't have the power to do that. But during the years, lots of things changed. So this is how the transistor counts in the microprocessors we use increased from the 70s to a few years ago. So in the 70s, so just after the white paper that we saw, we were in the range of the thousands of transistors in a chip. Now we are in the range of the billions of transistors in a chip. So this means that we have several order of magnitude more power that the people had in the 70s and in the 60s. And also new architecture came around. Normally, we use processors, the CPU, that are oriented for speed. So usually we have very few cores that are very fast. So Intel processors, the most enterprisey processors, reach nowadays 24 cores, and they are very fast cores, a few gigahertz. But at the same time, people playing video games in their home actually helped neural networks improve a lot, because playing at home with your video games, you had the problem of having a very good graphic rendering, and graphical rendering of the screen is something that can be made very easily in parallel, because you can render every part of the screen aside from the other, and this also can extend to 3D graphics. So a different kind of processor started to evolve, the graphical processing unit, the GPU. And now we have processors like the NVIDIA K80 that has almost 2,500 cores. Those are much slower cores than the core that you find in a normal Intel processor, but the overall power of these GPUs is much higher than the power of a normal CPU processor. And people started to think maybe we can use GPUs to do other things that can be computed in parallel. And they started to think about new algorithms, using the GPUs, and in this range of period from 98 to 2009, some interesting papers were published. So Lecan, Hilton, and Benjo, they published different approach, different algorithms. They managed to have backpropagation, that is the algorithm that we use to train neural network, work with very deep networks, because you have lots and lots of layers, but you can still backpropagate the difference and learn the right weights to use. And this created what now we call deep learning. And deep learning basically means that we are using deep neural networks, and we are also able, this is very important, to train these deep neural networks. So algorithms, science, and computer power and GPUs. And then people started to think maybe we can do different things than just add layers of neural networks. And they started to think, how can we improve image processing? And here I want to introduce a concept that seems a little bit strange, but then it will fit in the story. It's the concept of convolution metrics. Those are also called image kernel for people that maybe has an image background. And convolution is a complex mathematical term to say when you have a function and you apply a function to another function. So basically, it's a function applied to another function. Let's take this picture in black and white. I'm from Italy and I'm from Rome, so that I chose a completely random picture for this example. And let's start with this picture. And Let's take a convolution matrix. This is actually a relatively small matrix. Can be 3 by 3, 5 by 5, 7 by 7. Any number can work, basically. And we will use this matrix, and we will apply this matrix to every pixel of the picture. And for every pixel of the picture, we will multiply the pixel and the neighborhood of the pixel by the numbers that are on this matrix, and then we will sum everything together, and we get a new value, and we will use this new value as the new pixel of the output image. So this example here is the example of the identity for the convolutional matrix, because you are taking the same value, 1, for the pixel, and you are disregarding all the neighborhood pixel because you're using 0. For people that studied linear algebra, you notice this is not matrix multiplication, and the identity matrix is completely different because it's a diagonal line of 1, so it's not matrix multiplication. For people coming from functional language, this reminds me a little bit when you have the map operator and you apply a map on a vector. This is a bidimensional vector, but in this case you don't apply the function only to one element of the vector, but to also the neighborhood of the element of the vector. So, of course, you can do more interesting things than identity. And if you start to look into not the central point of the, and you look at the surrounding neighborhood, you can use this very small matrix to find the left edges of a pixel, because you look what's on the left, you look to what's on the right, and you use the minus to subtract them. And of course, if you invert the sign, you get the right edges. If you turn it 90 degrees, you get the top edges, or you get the bottom edges. And you can also use random values here, and you get some strange picture in output that will look for something inside this picture. And this is the idea of convolutional neural networks. The idea of convolutional neural networks is that you take an image, then you create some random matrix, usually lots of them, and from one input picture you create all these different representation of the picture, and then usually in the output you take this output picture, you make them a little bit smaller, more for localization and memory than for other reason, and then you apply to every picture again other matrices, and you get from one picture you get, for example, 10 pictures, then 100 pictures, and so on. So you get lots of versions of the pictures, always smaller. At the end, you get very small pictures that you connect with a normal layer of neural networks. So you start with one picture, then you get different pictures that maybe look for left edges, right edges, or different things, and you go on. Actually, the values of this matrix are random at the beginning, and then you use the training of the neural network to find values that make sense for your use case. So this is interesting because you get something completely different from normal neural networks, but it works very well. So this is ImageNet. It's one of the industry challenge where academics and private companies compete in image classification. So here you have usually hundreds of thousands of pictures, and you want to understand what's in this picture and classify the picture with some category. Like this picture, there is a person, this picture, there is the sea, there is a building, or something like that. So it's really trying to apply vision in understanding the category, giving a textual representation of an image that you get. And 2012 was the year where convolutional neural networks were introduced. And we basically moved from a 30% error, 25-30% error, that means lots of errors, to we dropped almost half. And then we are, all the other years, we still evolved on the CNNs. And now we are around a 3% error. And error in this use case is not linear. So if you get 30% error in image classification, you never use it because it's almost random. But if you get 3% error, it starts to be something that you can use for interesting use cases. And this is the paper that introduced this concept. It's described the model. They used 8 of those layers that I was describing of image convolutional matrix. And overall, they have 60 million of parameters to find when you train the model. This is just to give you an idea of how complex and computational intensive it is to train a model. And to train 60 million parameters, you also need a lot of data, because you know, if you don't have enough data, then the training can just turn around your data and do overfitting. So you fit completely your data, but then if you get a new picture, it doesn't work at all. The year after, someone made a very interesting article describing. He said, now we have this trained network that works, classifies picture, and we have some values that these metrics were found by themselves by training. But what are these metrics looking for? So basically, he tried to visualize the matrix and also to see which pattern in the picture were reacting with this matrix. So to find what was firing these perceptrons. At the end, there's still this concept behind. So what they found was that the first layer were looking for very basic information. So the first layer was looking for diagonal lines, horizontal lines, or something like that, similar to the edges example that I showed. Then the next layers were looking for something more interesting, like the second layer was looking for circles or stripes. The third layer was starting to look for tiles, was starting to look for objects that maybe are round and orange. And then the level 4 start to look for dogs, start to look for clocks. Level 5 starts to look for people, starts to look for the eye of birds. So this is completely learned by the neural model by approximation and trying to reduce the error in the classification. And actually, if you look at a convolutional matrix, you have that all these first layer that are used to find features are actually quite abstract. So if you want to replace the ImageNet problem with a much simpler problem that is very much used by academics, that is this a cat or is this a dog? It looks a very easy problem for us, but it's not for a computer. You can reuse the same values that you already found for another visualization problem, like the ImageNet, and then you only retrain the final layer. So in a way, it's like if you learn how to see, then you can use the same values for different use cases, not just to see in the ImageNet composition, but to see if this is a cat, this is a dog, and other use cases. And this also means that if you have a vision problem that you want to solve with a neural network, you can take a pre-trained model that maybe requires 30 days of parallel computing, but you take the result and you just retrain the final 1 or 2 layers, and with a couple of hours of computation, you can solve a vision problem building on top of a pre-trained model. And also, over the years, they started to see maybe we can create something different also for memory, because all the examples that I showed up to now, they don't have memory. So if you give a picture, they will give you an output. But if you show different pictures, there's no context. And if you want to solve other problems, such as natural language processing, context is very important, because if I say a word in one context, has a completely different meaning than if I say the same word in another context. So you need a neural network that has memory. So instead of having a feed-forward network like normally we had up to now, they start to say, okay, maybe the network itself can send some feedback back. So some neuron is connected back to the neuron at the beginning. And these are called recurrent neural networks. And the most common example is called, the most popular example is called long short-term memory, where basically you have the CT at the center is one normal neural network, can be 1 neuron or 100 neurons, but you surround this with some gates that those are variables that decide how much of the information that is output of this subset of my network goes into the memory, how much must be kept and how much you must forget, and then how much goes actually into the output that I want to collect. So with these 3 values, you can balance and keep some values inside the network. And so if you have, for example, an audio stream, you can keep some values, and you can use this for learning how to transform a voice stream into text. And there are really now tens, hundreds, thousands of different neural network architectures. This is a company in the Netherlands. It's called Asimov Institute. They are interested into using neural networks to create new content in the creativity side of neural networks. It's an interesting topic. And they created this map where you can really see how much you can do with different topology of neural networks. And this is the final example that I want to show to you, that is generative adversarial networks, GANs. The idea here is that you have two different neural networks. You want to use unsupervised learning because maybe you don't have all the information. And you train this network by having these two networks compete one against the other, similar to what was done with the checkers example at the beginning when you were competing one program against the other. So in this case, you have a series of real pictures and a generator neural network that should generate pictures similar to real pictures. So at the beginning, this generator neural network will create random pictures. And then you feed randomly a real picture or a generated picture to the discriminator neural network that must understand if this is a real picture or not. Is this real or generated? If the discriminator fails to understand if it's real or not, it will get a feedback and will try to improve for the next time. If the discriminator is correct, so it can classify, for example, that this is a generated picture because it's not a good picture, then you get a feedback to the generator network to improve and generate better pictures again. And in this way, you can train with unsupervised learning neural networks. And this was introduced by Goodfellow in 2014. And in these pictures, the images with the yellow box are generated by a neural network. And as you see, we can generate very easily numbers, faces. When you go into more complex objects, especially if you zoom, you see that the pictures are not really good. But it was a good beginning. Then, on this approach, last year, so we are almost on the front line of research here for neural networks, this adversarial network approach was used to try to represent complex concepts. So the idea is, okay, I'm capable of generating a smiling woman. I'm capable of generating a neutral woman and a neutral man that simply don't smile. And then I can use this model to say, okay, take a smiling woman, remove a neutral woman, add a neutral man, and what you get is a smiling man. So you can, a computer, generate a picture of a smiling man that has never seen before, because it was not in the training. And in the same way, you can add glasses to people that has no glasses. This is interesting because it's really generated by the neural network without further input. So why I'm here today to talk about these things? Because we really apply artificial intelligence a lot inside Amazon. We use it for discovery and search of products. We use it for the fulfillment. So if you order something on Amazon, for example, we have robots that use complex algorithms to find the right path, the best way to bring the stuff from the fulfillment center to the delivery side. We add machine learning to our products, and we also have a product that is entirely built on top of machine learning. That is the Amazon Echo and the Amazon Alexa platform. So maybe you know it, but...
I can play music, answer questions, get the news and weather, create to-do lists, and even read books for you.
I don't know if you heard something or the audio was working. Did you hear it? Okay. So this is the Amazon Echo. It's an hardware device. I have a small one here, but it's also a platform where you have APIs that are free to use. So if you want to use these APIs, there's no cost. The Alexa voice service, you can use it to integrate the same voice capability in a physical product, such as a car, a refrigerator, or you can use it to add that to a mobile app or a software application. On the other side, you have the Skills Kit. The Alexa Skills Kit is an API that you can use to add a new skill, to add some new skill to the Alexa platform that you can use to interact. For example, in the US, Uber added a skill where you can use Uber to order a vehicle straight from Alexa and without having to reach for your mobile phone. And we also use artificial intelligence within AWS. So we have instances, we have images that you can use, and we also are baking an open source project, this Apache MXNet, as a framework for deep learning. So, for example, the P2 instance, they have the K80 NVIDIA GPU that I mentioned before. So you can have from 1 up to 16 of those cards, so up to 20,000 cores in a single virtual server. And the cheapest one here starts with 90 cents US dollar cents per hour. So if you want to do some deep learning with these instances, you can use it for 2 hours and it costs like a coffee. We also have the possibility to attach GPUs to an instance. So if you want to go cheaper, you can use a normal instance, and when you need a GPU, you attach it elastically, and then you detach it when you don't need it anymore. We also are trying to move it forward. There's a new trend in the industry to move into hardware. We normally notice in AWS, we reach a scale where we are moving stuff into hardware, like all the networking software that we have, it's now into silicon, it's not running into software because it's more efficient. Usually moving something into hardware is 10 times faster and 10 times cheaper if you reach the scale. But normally customers, they don't have the scale. So we launched this new instance type that has an FPGA, a field programmable gate array. A field programmable gate array is a silicon that you can program on the field. It's like if you have the AND OR and you can program them, the silicon will change, and then you have an hardware chipset that you program that you can use, and it's much, much faster than a software program running in a CPU. Usually you have a language similar to C to program these devices, but you can also use images that other people published that can solve similar problems. This is the open source project that we as Amazon are supporting. It has been accepted by Apache, the Apache incubator 1 month ago. It's MXNet, and we chose this project because it's portable, it's efficient, it's used very little memory compared to other softwares, and it's also very scalable, both if you have multiple GPUs inside a server and if you use multiple servers together. So we really like this, and we are trying to use this more also internally. We have an image that you can use if you start a virtual server on Amazon, where most of the software that you normally need to install to do deep learning is already there. So if you will follow a tutorial, you can use this. There's no cost in using this image. You only pay for the instances that you use. And you have all the drivers from NVIDIA, everything, all the middleware software is installed. And then you have the most popular frameworks, so MXNet, but also Caffe, TensorFlow, Tiano, Torch, Keras, and so on. You can also use Apache Spark. It's another possibility for machine learning, not neural networks, more on the traditional side of machine learning, because there's a very powerful machine learning library. And we also launched a few services, high-level services that use all the things that we saw, but with a simple API for developers. It's part of what we call the Amazon Artificial Intelligence Initiative. And the first service is Amazon Rekognition, that does image recognition. So you can use this service to look in a picture and find the objects in this picture, similar to the ImageNet that I was mentioning. So this is from this picture, you see that there is a car, it's outside, it's daytime, someone is driving. It also can look for faces, can understand if the face is male, female. It can also look into the emotion of the face. She's happy, she's sad, she's angry. And it can also look into face detection. So you can create a collection of faces and do face detection. This is starting to be used by VIP use cases. So for example, if you are at an hotel and you want to do a check-in of your customers, if the customer have some membership with your hotel chain, maybe you already have their picture. When the customer arrives, you can recognize the person and find everything already there. So, okay, you prefer this kind of room, I already did the check-in and everything, maybe just check the passport for confirmation. And we use the convolutional architecture that I described here. We can just have a quick look. You can use Rekognition. The first year, you can have up to 5,000 pictures analyzed for free without any cost. So you can experiment with Rekognition without any cost. And the idea here is that you provide a picture. I'm using the graphical user interface, but of course, there's an API for most common languages, such as JavaScript, Java, Python, Go, and so on. You give a picture and you get an output that actually is a JSON payload with a level of confidence. Like in this picture, we see that there is a skateboard with 99% confidence, people with 99% confidence, a car with 91% confidence, and so on. And you can also do face analysis, like in this use case, if we look at the JSON payload, let me extend it a little bit. You can see that you get an age range, the possibility that she has a bird, or likely not. The emotions, she's happy, 93%, calm, 28%, angry, 1.4%, so probably she's not angry, and so on. You also get the face landmark. So, for example, you can easily put new sunglasses on top of a face because you know where the eyes are. One very interesting use case is from a person I know. What we did, he needed to anonymize pictures, so remove the faces. So he created a trigger on our storage, Amazon S3. Every time someone was uploading a picture, he was looking for the faces, replacing the faces with emoticon, so big smile, but it was looking into the emotion. So depending on the emotion of the person, was using the right emoticon. So a sad one, a happy one, a smiley one, and so on. So it was an interesting and very easy to build use case. The second service is Amazon Polly, and Polly is the voice of Alexa, but she also speaks 24 languages, so lots of languages. You give some text or some markup languages. We support the speech synthesis markup languages, is a W3C standard, and you get the audio of the voice. So this is how it works. You give a string of text with symbols, like this one. We find out which are the words behind the symbols, like the greater than, it's more than, and the percent symbol. When we have the words, we look for the phonemes in the words. That depends, of course, also on the language. And we also look into where the words are used, because words in English have a different pronunciation, and also in other languages. Like live and live, they are written the same, but I live in New York, but this is broadcasted live from New York. So you need to understand the role of the word in the sentence. Then we also apply a prosody contour. This is important, but when we speak, you usually grow and go down with volume, and this is making our voice more human. If we are really monotonic, usually this is a very boring speaker, so I hope I'm not one of those. And so basically what we do, we look for the speech units, depending on the voice. We build the sentence, we apply the prosody modification to give some natural flow, and then you get the output.
Market grew by more than 20%.
I don't know if you heard it. Yeah. So you heard it started high, then went down, so it wasn't completely monotonic. If you have time, try with a long paragraph of text, because you can really see how the flow is changing. And the third service that we announced is not Amazon Alexa, because that was already available, but Amazon Lex. It's what's inside Alexa. It's an engine that can help you build a bot that can work via text or via voice. So you talk with the bot will collect information and eventually use Lambda functions on AWS to fulfill the requirement. So the idea is that you have a bot that can have multiple intents. Each intent is like an action that you want to do. For example, if you create a booking agent bot, it can book hotel and it can book cars. You have two intents. Each intent you give utterances, so simple sentence that people can use. And then you need the slot. The slot are the variables of the intent. So if you want to book an hotel, you need to know the town and the dates, otherwise it doesn't make sense. And when you have all the information, you have the fulfillment. The fulfillment will do something that you need. So for example, if you say via voice, book a hotel in New York City, this will be transformed by the automatic speech recognition into words. The words will go to the natural language understanding module that will map this to intent. He wants to book an hotel, okay, booking, and we'll start to look for slots, for variables. In this case, one variable was passed with the initial sentence, so New York City. So we create the intent and we start to populate the slot, and then we will ask other questions to fill the other slots, like the date, check-in date, check-out date, and then usually this is good for bots. You ask for confirmation, maybe something was not understood correctly, and then you have a Lambda function that will do the actual hotel booking. And then Polly will render the output back into voice, like, okay, your hotel has been booked. This is also integrated with our mobile hub. This is a free-to-use tool that generates all the code for a mobile hub. So if we want to use this in a mobile application, we generate all the code for iOS or Android for you, no cost, and you have a mobile app that can do these kind of things via voice or via text without writing one line of code, so that as a developer you can focus on what's important for you. And the last one is Amazon Machine Learning. This is a more extensible platform where you can train model, create a data source, and everything can be done via the console or via APIs, like I'm using Python here. Then you can explore and understand the data. You can train your model, like I said before, and you can also use an API. You can evaluate the model. This is a very important step because normally when you have an error in machine learning, it can be a false positive or a false negative, and those two things can be really different depending on your use case. So for an email, a false positive means a spam. I think this is spam, but it is not. So you lose an email, for example. If you use machine learning in healthcare, for example, to understand the risk of people of having some specific illness, a false positive is not wrong, because if I say maybe you are at risk, you take another examination. But if I say I have a false negative, then maybe you say, okay, I'm not at risk, I'm not taking another examination, and so this can be risky. So in healthcare, you don't want to have false negative, you prefer to have false positive. So this is a very important tuning step in machine learning models. And then you can have batch prediction or real-time prediction, where you have a predict API that you can use to do prediction. So let's do a quick demo, and then I finish. I always did the example of bike sharing. So I want to build a model of bike sharing. The town of Washington, D.C., they released their data. It's available, and you can download it. I look into how the users were using their bikes. I discovered that casual users are using the bikes differently than registered users, so I created two different models, one for casual users that doesn't have a subscription and use the bike mostly on weekends, and registered users that use bikes mostly for commuting in the morning and in the evening. It's better to have two simpler models than to build one more complex one. And then I created a skill for Alexa that will use this model and a weather forecast service, because the weather is an important parameter to understand if someone is using a bike or not, and it's using this training model with real-time prediction. So let's see if this works. So, Alexa, good morning.
Good morning. Happy birthday to author Bernard Cornwell, without whom we would have no Major Richard Sharp. A character so powerful that he even survived being played by Sean Bean.
This is an interesting intro. So, Alexa, what's the weather like in Zurich?
Currently, in Zurich, Switzerland, it's 15 degrees with clear skies and sun. Today, you can expect clouds and showers, with a high of 17 degrees and a low of 4 degrees.
Quite off. Alexa, can you play Michael Jackson on Spotify?
Playing songs by Michael Jackson from Spotify.
Of course, the choice was easy. Alexa, stop. Now let's use the machine learning model, that is more interesting. So let's use it as an application. So Alexa, open bike sharing.
Welcome to bike sharing prediction. You can ask me how many bikes will be used on a date. How can I help you?
How many bikes will be rented tomorrow at 8 a.m.?
It will be a Friday. The weather will be partly cloudy, so I expect that 312 bikes will be used, 44 from casual users and 268 from registered users.
And you can also interact directly, so you can say, Alexa, ask bike sharing what will happen on Sunday at 12 p.m.
It will be a Sunday. The weather will be clear throughout the day, so I expect that 162 bikes will be used, 56 from casual users and 106 from registered users.
So as you see, you can really build interesting interaction models with some smartness, just plugging a few building blocks together. So what final suggestion, if you find a service that already does what you need, like image recognition or voice recognition, use it. Otherwise, look for platforms or engines that can use with your data. And we are really living in interesting times, so I'm really excited about machine learning, IoT, wireless. This is really changing the landscape, creating new capabilities. And I think it's our duty as developers to be updated on these topics, because we must understand what's happening to build better and smarter applications. So thank you. I overran. I don't know if there is no time for questions. No time? So if you want to reach to me, Danilo is my Twitter handle, and it's also my email at amazon.com. Thank you again.